as visitors in 1991 at the Weizmann Institute, and correspondingly in 92 became members of the Weizmann Institute. Gregory, however, had to pass the whole staircase, so originally as just from the beginning, then to get tenures and to get to be promoted. And at a certain stage, he was the head of the department of complex system. At Weizmann physics faculty is divided on 3 pieces, and one of them is called complex systems. And complex systems include cold atoms, AMO, include statistical physics, studies of brain, including all kinds of theory and measurement, and also include the hydrodynamics, physics of polymers, and so on. So Grisha, from more than 5 years, was the head of all this kind of community, which is, of course, was quite variable in the direction and have some different interests. Okay, so Grisha is famous. What is he famous for? Soon after he joined Weizmann Institute, he, together with some colleagues, mostly from Landau Institute, started to attack a well-known problem in hydrodynamics, which is called Kreisman problem, or the same thing as the problem of passive scalar. And they solved this problem. This problem of passive scalar, the Kreisman model, is for hydrodynamics, for theory of turbulence, is something like Ising model. So namely, it contains all the non-triviality, but on the other hand, is simplified enough to just to be analyzed and to be solved. So that's what they did, and they found plenty of important things. Namely, they eventually understood why simple treatment of Kolmogorov approach have some limitations. What are anomalous dimensions and all these kind of things? Not speaking about all these buzzwords like direct cascade, inverse cascade, and so on and so on. So all those was there. Now this progress, in turn, boosted the enormous activity in numerics, which in turn just discovered plenty of interesting details and so on. And Grisha led all these studies as the theorist. So, and eventually all that turned to studies of climate. So conferences which Grisha organized and which he gave talks and so on, they can be looking like that. For example, it could be a talk in the same year which sound like that. Multi-point correlation and symmetries in turbulence. Symmetries and operator product expansion. And in the same years, how rain starts, who drives the weather changes. So all that is in Santa Barbara, in Simon's sensor, and so on. So all that appears to be that absolutely abstract questions which are interesting for high energy physics appear to be relevant for something as practical as climate and so on. So Grisha had some important visiting fellowships, namely he spent sabbatical in the Institute of Advanced Study in Princeton, in the Institute of Theoretical Physics in Santa Barbara. He has some visiting professorships in École Normale, in Simon's Sensor, something which is a Levelholm visiting professor in the United States. So he is a well-established and well-known person. So it is not surprising that a personality with such energy runs marathon. But what makes me to be really puzzled when I found out that at a certain moment he became a head of trade union of scientists at the Weizmann Institute. When I asked him, what for you are interested in this strange business, the answer was that, you know, there are all these kind of things which are typed in small letters who nobody reads and nobody knows. I would like to know, to understand how all that works. So I have a humble suspicion that it is experience with this kind of hidden fluxes of this hidden information, which bring us for today's talk, which is how the information, theory of information connected.
Very profound guess, Sasha, very profound. Yeah. Thank you. Thank you, Sasha, for this wonderful introduction. Happy to be here. Like this place very much. It's excellent for marathons. Latest. So it will be a very elementary talk. It's a blackboard chalk talk intended for students, and I very much ask you to interrupt me with you know, technical question and all. The plan is as follows. Would look very strange. So first, I remind you about second law of thermodynamics, which you all know. I just give a brief reminder in terms in which I would like to discuss it first. The second part, so this is the first. The second part is not this. It will be informational theory presented in a most elementary way. It's very easy for physicists to learn information theory in 15 minutes because it's nothing but statistical physics, just some things are named. Third will be a little bit of turbulence, but also we'll return to second law of thermodynamics. And you mean that it's not very... Okay. Good. So that's the plan. So let me remind you a little bit about a puzzle. And I still remember how when I was student back in Novosibirsk, how they tortured us teaching statistical physics. There were all paradoxes. There was paradox of this and paradox of that. And I remember this, I really did not like it. I think that science, it must be trivial. And that was all very non-trivial. And people were proud that this is non-trivial. What really I want to tell you the way that I think that people will learn how to make it trivial and very, very powerful. The moment you make something trivial, you do understand. So let me remind you on the language in which I think there are many ways to tell the story. So one thing is that, let's say I have a space of all momenta and coordinates, and it has 2 times 10 to 23 dimensionality. And in this space, I am interested in the density, a probability distribution of this vector, and as a function of time. And because it's a density, then it satisfies the equation of which is called continuity equation. So it's just rho times v. What is v is again a vector of this dimensionality 2 times. It's x dot and p dot, all the coordinates. And as we know that x dot is a derivative of Hamiltonian with respect to pi, and pi is minus derivative of Hamiltonian with respect to qi. Those are my canonical coordinates. And so now when I look into it, I've realized that if I look at it as a fluid mechanicist, the flow in this space is incompressible. What does it mean? Vex is qi pi. Yeah, thank you. So if I would compute divergency of v, which is dv qt over dq plus dv theta over dp, this is 0 because this would be a derivative of this with respect to q minus derivative of this with respect to p. So if I write this continuity equation, as we say, in the co-moving reference frame, namely as a material derivative, which is just d rho dt plus v grad rho, it's minus rho div v, and it's 0 for Hamiltonian flow. Sometimes it's called Liouville theorem. So you conserve measure. The way you move, if you expand in p direction, you contract in q direction. Good. And now, if you are interested in quantity, which is called entropy, and it could be expressed in terms of rho in the following way. You take rho, you take logarithm rho, and because I'll be doing information series, this log will be not natural log, it will be log 2. Anyway, any log you take, you integrate dx. Now it's straightforward to show that this quantity also conserves. Not only it conserves as a whole, but it's integral in any PQ plane. So for any direction, you have PI and QI, and it's also straightforward. So you write ds dt, and this is, of course, you differentiate this, and it will give you rho dot dx, and it's apparently 0 because your total integral of probability is conserved. And then what you get when you differentiate this, you would get log rho divergency of rho v integral over dx. Then you integrate by parts and integrate by parts again, and you get this divergency acting on v, but dv is 0. It's called Liouville theorem, and it's kind of well known that Hamiltonian evolution conserves density of any element, but it also conserves integral, which is entropy. Good, that's Liouville. Then comes Boltzmann, and he said, let's look at it from a very, very restricted perspective. So let's take this rho of all pi's and qi's, multiply it by delta function of p1 minus certain value p, and integrate over all q1, qn, and over all dp, dpn. I intentionally write it like this instead of dx. So this would be function only of p, this value, end of time. It's a one particle probability of having momentum value p. Can we derive equation on this quantity? Well, we can. It depends on the form of the Hamiltonian. Let me just have it here so that I would use right notation. So we consider a simplest Hamiltonian we can imagine, which would be a sum of pi squared over 2m plus some potential. So we assume that there is pair interaction between particles, and every particle just has a momentum. Then what we need to do, we need to take this d rho dt and integrate it over everything except one momentum. Okay, so that would be. So if I would now write d rho of p t dt, what I would get, let me just make it fast. So I would get an integral over all my coordinates, delta function of p1 minus p. And what would be standing here, it's a time derivative of rho, which would be derivative over q, namely that will be pi squared over 2m d dqi rho, rho of all x. But this would be 0 because this is the total integral. So what would be remaining here is a part which is related to u, and it would have the following form. It would have du dqi, d dpi, d dpj. And here rho of all x, including the coordinate. So now you see that what actually stands here is two-particle probability distribution, which is, so when you integrate over everything else except I in J, in this row still will be two coordinates. So you can kind of symbolically write it as an integral rho P Q P prime Q prime and some function which depends on, which actually depends on the form of potential. There is now no J. There is this P, okay? And the rest is now integral over dP prime, dQ prime, okay? So here was the sum over all J's. So all were integrated except this first particle, but this brings a second particle over which I need to integrate. So if you wish, this is I and this is J, which was standing here. Okay, so this is two particles. And then Boltzmann made a very crucial step. He said, now we cannot handle it generally. We need to consider some very, very oversimplified situation. So let's consider that our potential is a very short range and our gas or whatever medium is very dilute. If it's very dilute, that what actually happens, the particles, this potential interact in a tiny region, and in between interactions, they fly freely for very long distances. And that allowed him to make a very crucial assumption that this two-particle correlation probability distribution could be split into product of two parts. And the physical assumption was that the particles that collide here came from such large distances that they are actually uncorrelated. Back there where they originated, the fact that they will collide was set somewhere there, but somewhere there was just randomly. They could fly in any direction. So what Boltzmann did, he split this on a product rho of PQ, rho of P prime, Q prime. That was a crucial step. And after that, he derived this famous Boltzmann equation. Let me write it here, d rho dt, again, of a momentum P. And it's some kernel which depends on the potential and has some property, and it has the following form: rho prime, rho 1 prime minus rho 1, and it describes the physical situation where you have particle with a momentum p and some other particle with a momentum p1, and what is called primes is their momenta after the collision, p1 prime. And this needs to be integrated over dp1, dp1 prime, dp prime. This equation now, if you look at entropy, which now is a one particle entropy of a single of this, any probability distribution has its entropy. You just take rho log rho and integrate. So if now I would call it SI of a single particle, if you now look at it as this rho log rho dp, then of course ds dt, it's so-called H theorem of Boltzmann. I won't derive it. It's a straightforward derivation. Could be shown strictly non-negative. As physicists like to say positive, it's non-negative. And yet, this equation increases entropy monotonically as long as we are not in equilibrium. In equilibrium, this is equal to this because the momentum are conserved, but generally not. So what does it mean? That the sum of Si minus Sn, a total entropy over there, let me now give it an index. Let's say we're God Almighty. At the beginning, we put all particles everywhere. absolutely uncorrelated position, give them absolutely uncorrelated momentum, and let it run. At this first moment, they are definitely equal to each other. We just designed it this way. Now, what we see that if we did not design them to have Maxwell distribution of momenta in uniform distribution in space, this quantity start to grow. Is not a thermodynamic entropy supposed to be extensive function? Something that, so the question is, does not this equal to Z? Is there any contradiction that there is a growth? So that's essentially the thing that I was tortured 40 years ago at my statistical physics course by Kotkin, and you definitely. And the answer to both questions is no. They aren't equal to each other, and no, there is no contradiction here. And there are many ways to sing this song. I will give you my way, and then I'll try to show you how powerful the instrument which appears out of answering this question, and how widely, from self-driving cars to black holes to market strategies, this instrument is applied, and it's called mutual information. So for this, let me tell you what is information. And again, this is not the only way to look at second law of thermodynamics, but this is a very powerful way. Yes? No. Boltzmann made. But what I'm saying is that it makes sense. I can create such a initial situation in which it would work, because I can definitely assume that particles are uncorrelated. And there are many, many subtle arguments. Just to give you a feeling, for this equation, the Fields medal was given in 21st century. So, I mean, mathematically, it's a very non-trivial transition from here to there. And there is a lot of subtleties. This quantity, rho, it fluctuates as crazy because, you know, it's a multi-particle distribution. So every particle changes velocity. It's a very fast fluctuating quantity. This is very slow. It's a one particle, right? It's already average over many particles. There are many, many subtleties involved here, and I'm not going to go into it and try to justify the derivation. I want to explain, I want to give you a way how I understand it in a very, very trivial way, and then use it, okay? So for this, I need information. So imagine that we have n boxes from 1 to n, and in one of these boxes is a candy. And I want you to tell me where the candy is, and you're telling me, and I want to quantify how much I got from you, except candy, right? So, and there are many ways to quantify how much information contains the message in the box number 5 or in the box number I. And one way to quantify, which happened to be invented by people who did not know all this story much, but it was 100 years ago. Shannon was 80 years, but there was actually Hartley and Fisher before, was let's count it by the number of questions for which I need to ask you, for which you would give me, let's say, yes, no answer. Yes, no is called 1 bit. That was invented actually even before by Leo Szilard in 1924, when he met Einstein in the corridor in Berlin, and he did not want to do his PhD, which for Laue gave him a problem. So Leo started to think about other things, and he was afraid to come to von Laue because he was Nobel laureate, and Einstein was a young fellow, and so he stopped Einstein in the corridor and told him what I'm about to tell you, more or less in this direction, which we now call the beginning of informational view on physics. And Einstein, after 5 minutes, say, well, that's nonsense. And after 10 minutes, he say, you sit and write your PhD. So what Leo did. So, and the idea was that let's count the number of yes/no questions, right? And most important questions like, you know, do you love me? It's yes/no questions. They all try to answer. It's complicated, but it's essentially yes/no question. And for example, we can ask these questions like right or left. Getting an answer with half the number of possibilities, right? And then we ask now, was a remaining, right or left? Again, we have. So it's clear that number of such questions is a log n by 2. Okay. If this n is 26, and we're talking about English alphabet, then the logarithm of 26 is 4.7. That's how much every English letter bring us. What it is? It's something little. If the moment that we talk about boxes and no other information is given, it's okay. But the moment we start to talk about letters, it's clear that letters are very different, right? So some are more frequent, some are less frequent. If our probability picked around only few boxes, then saying about these few boxes would give not much many information if it were some improbable boxes. So let's then look at it and ask if I have probability distribution, namely for every box, there is a probability on average that the candy will be in this box, or that letter K or L would appear in a long message. And then Shannon, that's already 1948, suggested to look at it in the limit of a very, very long string of letters. So imagine that I would get the first and n string, and then I ask how much information this string brings to me. Now I know that the first letter A appears with the probability PA, and then the last letter appears with the probability PZ. So I know how many times every letter appears. What I don't know, what any message brings me is the order in which my letters appear. So I need to ask how many such orders. That's a choice, that every message is a choice out of orders. So apparently the number of orders is C of n, and here is P1 and all the things, which is just n factorial divided by P1 n factorial, Pn n factorial. If you take a log of it, you would get, non-surprisingly, Gibbs entropy, because that was Boltzmann entropy. And what we get using a formula of Stirling is this formula. So what we obtain is that this quantity is a rate. You can say that this is how much information per letter, because it's proportional to the number of letters, right? This, incidentally, for English language is 4.1. Is it all we can say about English language? That is its entropy? Or there is something else? You see, every time we say that we know something, diminishes the amount of information which we obtain, because we already have some priors. What else do we know about English language, which dramatically lowers this number? For example, probability of U following Q is almost unity. Well, there are few foreign words in English, but generally everything you've got from Latin is Q followed by U. This U does not appear. This is Qatar and Katif. One is from Arabic, another from Hebrew. But generally, so what actually exists and very important is, and this is a crucial step, is a transition probability, a propagate, right? So there is for every letter, actually we'll probably write it here. There is a probability of I of J following by I. And this is something which is an extra information. Incidentally, this is a matrix and Pi is a vector. Are they independent? Of course not. In this matrix, actually the vector of your probabilities is an eigenvector of this matrix with a unit eigenvector, And Google's made their first $1 billion was made out of this formula. It's usually I teach at the end of my course how PageRank algorithm was born out of this formula. Anyway, let's characterize now our strings by this. This is a probability distribution. For every I, its sum over j is unity, right? So every letter is followed if you sum over all. And so you may now define a respective entropy, which would be a P of ji log P of ji. You need to sum it over j. That would be a normal entropy, but it is for every I. So if you really want to make a average characteristics of you need to sum it over pi now. And this is called conditional entropy. It's written like this, but it's not a function of j and I. It's just a number for every letter. And for English, it's summation over I and it's summation over j. Absolutely. So what stands here is actually probability of ij, which is the probability of I times probability of j under condition of I. It's called chain rule. Okay, but this is, of course, asymmetric. And generally, this is not a symmetric matrix. Sometimes it's symmetric. It's called detailed balance. Of course, it would be an equilibrium. It's not. It's a number. Yeah, but let me put it like this. What I want to stress, it's a conditional entropy. For English language, by the way, it's 1.5. It is a minus signs everywhere. Thank you. Yeah, and of course, if you compare now it's actually lowers to 1.4, but by some multi-letter correlation. So essentially, this gives you most of the internal information. Of course, Shannon studies all the, but this is the most important for us. In particularly, there was this famous poster in a New York subway. It's 70s. There is actually a poem which starts like this. Some poet. It's if you can read this. Advertisement for which job? A secretary. It was very well-paid job at early 70s. Some places still is. And this was real, and it was actually inspired some point. Just Google it. I mean, there is a beautiful literature around it. It tells you that redundancy of English language is almost any language, but in English, it's an old mature language. It's even more, about 3. So you can wipe out 2/3. Now, what it has to do with all this physics and all this stuff? Let me make one more step, namely use this. And now this is a very, very useful thing which people apply everywhere, in particularly when I am looking at this transitional entropy. Let me just generally, and it's not Alice and Bob. There's H bar will be 0 all the time, but the meaning is the same. I would have an input B and output A. And the generality is total. It could be your atom or candy in a box, and it is your message. It could be your prediction, and this is the reality. It could be just a message. So this is what was sent, and this was what was received through a noisy channel. It could be just a retrieval from memory, because memory is a message in time, not in space, right? So you wrote something, and then you retrieved it later. So now I want to know this has some probability distribution. And this has some probability distribution. Moreover, there is some conditional probability and conditional entropy remaining exactly in this way. Now I want to know how much now, and this is, of course, famous Shannon noisy channel theorem, how much on average this channel brings. And for this, I need to say that before I get a message, uncertainty was S of B. And after I get a message, a certainty is S of B and A. Right? So now, this is what is the message brought, and it's called mutual information between B and A. Let's now look at it in these terms of probability. Now, if you write it, it would be sum over all I and j, probability of AI, Bj, logarithm of probability of Bj, AI, of probability of B. Because I took this and this gave me this in the denominator. But chain rule tells me that this I can write as AI Bj divided by P of A in its symmetric completely. And of course, it's equal to S of A plus S of B minus S of A and B. And now it very much reminds us what we actually have seen in this, where is, anyway, the sum of Si minus a total S. Okay, so this combination, the sum of individual entropies minus the entropy of the adjoint distribution, it's an absolutely universal object. It appears over and over again. It's actually a little kind of particular case of a little bit more general quantity, which is sometimes called Kullback-Leibler divergence or relative entropy, namely that you have a probability distribution Pi, but you don't know it, so you make a hypothesis. All this is kind of a very practical, like experimentalist. Most of a reproducibility crisis, which also a little bit in physics, but of course it devastates many other disciplines because people don't use correctly these simple formulas. But so you guess that your probability distribution is Qi. How many experiments you need to make to see that this is wrong and how wrong it is? So now, if you get some result I, it would appear with a probability that I would use right notation, right? So it would appear Pi n times. But what you judge its probability, you say that this is Qi in this number of times, because you assume that every time it appears independently, it appears that many times, you assume that its probability is this. So if now you say, what is my probability of, again, n string like this, then you will see that you need to take product of I, of Qi's in this power Pin, right? And multiply, non-surprisingly, by the same combinatorial factor, which is how many, so you would get n factorial, P1n, Pnn, factorials. And again, if you write it as an exponent of something, you would obtain here a beautiful formula, which is now the most general part of it. Essentially, mutual information is when you assume that your Qi is a product. So it's a particular case of this relative entropy. And I won't probably go into it, but I was going to tell you how market strategy works, because it is this quantity, which is called relative entropy or Kullback-Leibler divergence, is determined how much you can earn if your probability distribution that you use is better than other market players use. It is this quantity P log P over Q. It's a very beautiful and interesting quantity. Okay, so now what I want to return back to physics and discuss how much of this quantity, which now, what all the algorithms, for example, of self-driving cars, they actually minimize this combination. This is totally universal tool. And of course, entanglement entropy is its quantum sibling of this quantity, right? And as opposite to entropy, all this, big ultraviolet divergence and other things, they cancel out. But now what I want to return back to Boltzmann and ask if it's important, how it explains the second law of thermodynamics. And now I return to your very right remark. So if at the beginning I created my situation that all particles are non-correlated, and then let time run, they start interacting because they do collide with each other. So the statement that Boltzmann made, that the one particle entropy increases, and the statement that Liouville made, that the n particle entropy stays the same, is a statement that mutual information, which is sum of SIs minus Sn, is growing. Yes, it does. So you may replace a second law of thermodynamics by a pretty trivial statement that the total entropy is conserved. That's true. Total entropy is conserved. And correlation between particle, if you start from uncorrelated situation, is growing. And that means that because the total, if this is growing, and this is growing, and this is conserved, or you can say that this is growing and this is conserved, and this is growing. So essentially, our second law of thermodynamics, the way we present it classically, it was a statement about something growing. Now we can say that it equivalently could be presented as a statement that we decided to renounce any knowledge about correlation. The moment we are interested in the additive quantity, this additive quantity is not a true entropy. It's something which renounces correlation. Then naturally it's much more. And whatever information you had, with time, its value decreases. And that's the different, and I don't want to go into subtleties, how finite coarse graining and exponential separation of trajectory, but this is the language on which to look at it. And I don't want at this point to be philosophical about it. I want to be technical. I want to ask now myself, can I apply it, for example, to turbulence or to other system and do the same? Namely, I would take a Hamiltonian, which is a little bit different. So I would consider just a classical waves, and they would have their interaction, which would correspond to a cubic term in the Hamiltonian. Something like this, okay? And now I can, of course, write dynamical equation, which would be just dA dt derivative of Hamiltonian. And it's more or less similar to, but it's more complicated technically. And then I may say that if I'm interested in the analog of Boltzmann equation, what it would be here. It would be an equation of AK modulo squared on the occupation numbers. If I call it NK, this would be an occupation numbers over wave vector. And I can write the equation dnk dt. And of course, it will be schematically proportional to V, imaginary part of A correlation function, exactly like Boltzmann got his closure problem to particle rho. Here I had a third moment. So I may write equation on the third moment, assuming that initially I had Gaussian uncorrelated waves all over, and obtain the following thing. How much time? Yeah, a little bit. So if I would just write, let me call it J, which is this A correlator. And it's pretty easy to get it. And this is 1, 2, 3, and this is 1, 2, 3. And delta is just omega 1 plus omega 2 minus omega 3. It's a resonant condition. And what I would get here is V and 1 and 2 minus N1 and 3 minus N2 and 3. That's a standard combination. Incidentally, Nobel Prize of this year was given to Hasselmann, who derived this kinetic equation for waves and used it for weather prediction, and not to Zakharov, who actually solved this equation, but it was derived by Rudy Parels in 1929 in his PhD. Everything was done by PhD students, including Zakharov solutions of this equation was also done as his PhD. Now, if you look at this third moment and plug it into this equation, you obtain this kinetic equation and everything is nice, even though it has this denominator, right? But now, if you look at which somehow for 40 years, we never looked into it, if you look at this quantity, which is D, okay? So what now I can ask myself, if I start from initial close to Gaussian distribution, and then I know that it acquires a third moment. A third moment, it's any cumulant means that this is non-Gaussian distribution. So I can measure the difference, the relative entropy between my distribution and Gaussian distribution, and it's not difficult to show that it's proportional to a square of a third cumulant. Now, if you look here and consider limit delta going to 0, this is just a delta function. But if you take it squared and consider limit, it would be t times delta function of difference of omega. You have a secular growing curve, which tells you the following thing, that generally, if you just impose any random distribution of waves, and the same, by the way, is true for particles, then you would see that your probability distribution will start deviating more and more non-stop, unless it is equilibrium. This combination for equilibrium distribution n k equal to t over omega k exactly give you this difference in cancel. And the same happened with the Boltzmann equation. Boltzmann equation done for rarefied gas, and it gives you virial expansion for the equation of state, and it works perfectly. This is only the first term of it. It's proportional to the pair collision. But there are also terms which could be like you have one particle and another particle come to it, then it scatter another, and then it goes back. So you can compute the correction to Boltzmann equation. It's called virial expansion. You can do order by order terms. And if you're interested in any equilibrium quantity, it's a perfect series in small parameters. The moment you try to compute diffusivity, any kinetic coefficient, viscosity, I'm not talking about turbulence. Turbulence is much more. You get what is called Dorfman-Cohen anomalies, namely, depending on your dimensionality, you start getting divergences. So actually, we understood all this after we obtain our own anomalies, namely that your probability distribution is actually very different from your assumption, even though kinetic equation works. If you're interested in kinetic, a Boltzmann equation, as long as you're interested in one particle distribution, it works well even in non-equilibrium. But if you're interested in the whole distribution, it's a very, very complicated thing. We're only starting to get an early feeling of what it is. It's most likely very non-uniform. It's, I mean, appearance of this large D, it's actually a statement that its entropy goes down. Because for a given n, and n is okay, n is correctly described by a kinetic equation. For a given variance, a Gaussian distribution provides for a maximal entropy. Whatever you deviate from Gaussian, your entropy goes down, which means that you, to keep system away from equilibrium, we used to think that you need to do work, but you may think different. You need to get some information about the system. And the more you deviate from equilibrium, the more information you actually need to use to keep it away from equilibrium. You may say that I'm extracting entropy. Yes, you're actually getting information. And this information is large, even for a system which is weakly interacting. You may think it's a perturbative system. It's a rarefied gas, right? It's a small parameter, it's a beautiful small parameter density, right? So if you take radius of interaction, cube multiplied by a density of particles, this is a small number. In this case, you assume the small amplitude. You assume that there is really dynamically, you have small interaction. If you're in equilibrium, all your corrections, all your cumulants will be small. If you are in a non-equilibrium, what we've got from here is that the cumulant would appear of higher order. There is no way to stop all this while you are still in the validity limit of weak approximation. And in this respect, if now I'm trying to make a kind of take-home lesson out of it, there's something that, like we all know since undergrads, and it's pays to look at it in you. And my own way of looking into it was through the lens of mutual information, saying that this is trivial. I mean, there's nothing non-trivial here, because if you really assume that initially things were uncorrelated, that will start to be correlated. If you don't want to consider this correlation, then some quantity would grow, because this quantity is not accounted for. But then when I realized it, I started using it in my own research, and I discovered a pretty unexpected thing about something that we did. I mean, with Zaharov wrote a book 30 years ago, and I thought that I would never work on wave turbulence because it's a trivial set of weakly interacting waves. Well, it is in equilibrium, but in non-equilibrium, it's something which we now start exploring. There is multi-mode correlation. There are many different beautiful things. Okay, so that's more or less the story that I wanted to tell you, and I think that every physicist needs to learn information theory. It's very easy. Thank you. Yes, there is nothing here that contradicts, because this is something about a very special case when you're close to integrability, and yes, and in this case, because what means integrable? It means that your measure already singular, right? So what here I'm starting from measure which is uniform. Gaussian essentially could take log of it's uniform, and I'm seeing how non-equilibrium make it very non-uniform. But integrable system already very degenerate. So there you actually, if it's exactly integrable, you just go on this torus, you know, over and over and over. And then you impose a non-integrable perturbation. So it's an opposite limit. You see how it starts spreading. So it's in a sense kind of a different limit of the story. Yes. Yes. This is a simple, straightforward, not I mean, Peierls did in 1929. He actually computed this formula and plugged it into this. Right now we give Nobel Prizes for such thing, but back then it was PhD. And but what I'm saying now is that if I'm interested not in a second moment, but in the whole entropy, and entropy knows about all cumulants, then it's something which is secularly growing in this approximation. And that was a surprise for me personally. Yes. Okay. No, well, first of all, I'm not sure that I'm kind of quite qualified, but I would say that I don't think that dissipation is always necessary to have a very, very non-uniform distribution, because essentially, and moreover, we're talking about gravity, which is a long-range interaction. And this is a huge difference from everything which essentially I was talking here and I was talking here is about short-range interaction. And generally, most of statistics that we take here for granted doesn't work for long-range interaction system. So I would kind of refrain probably from commenting. Yes. Yeah. No, essentially any closures that we use the second moment, or few second moments. Second moments are good for Gaussian distribution. The Gaussian distribution is completely determined by second moments. Okay, the moment that we are interested in what is the real distribution, it is non-Gaussian. And it may be for engineering reasons, you don't even interested in this high cumulants because you're interested in energetic balance. But the moment you start interested in rare fluctuations, so this is the way to look into rare fluctuations. But the new thing here, Diego, is that it's not only about how it non-Gaussian fluctuation on a given scale. What essential here is a multi-scale correlation. For me, it's a new thing. So I never asked myself how different wave numbers actually are correlated. I always was asking about, what is this deep into cascade, how non-Gaussian it is. Now I see that it's, to have all this entropy going down, I need this multi-mode correlation. This would be very interesting to see experimentally. Of course, random phase approximation is here because when you wrote the equation on the third moment, you get fourth moment. When you decoupled it through the product of two, then you use random phase approximation. What I am now telling you that this random phase approximation does not work uniformly on every cumulant. If you're interested in the cumulant number 3, 5, or even fourth cumulant, it works worse and worse. Okay, that's a statement. That the random phase approximation works well if you're interested in the second moment. Because, well, whatever, technical reason. But it actually does not work the moment you start computing higher cumulants. Landau Lifshitz actually has such statement. Yes, this quantity sits on high cumulants. This quantity tells you that even though when you look at occupation numbers, everything is nice. Why it does not work? Yeah. Because if you're interested in occupation numbers, everything is nice. If you're interested in Boltzmann one particle distribution, everything is okay. The moment you try to compute something non-equilibrium, you need to do expansion and you see that it does not work. There is no analytical expansion in small parameter in non-equilibrium. That's a simple message as theoretician to theoretician. In our case, the smallness of nonlinearity is multiplied by a Reynolds number, by the length of inertial interval, right? So I break equilibrium, namely I pump at this scale, I dissipate in this scale. This gives me a Reynolds number, the ratio. So my small nonlinearity is multiplied by this big number. And that's it. You don't have now expansion of your small parameter. So that makes it, huh? Reynolds number. It's a ratio of Reynolds number. It's a ratio of a pumping scale to the dissipation scale. That's what is large in non-equilibrium. But even in a simple case of that the Dorfman-Cohen. What they discovered a very simple thing, that if you write an expansion, if you take a dilute gas, a very rarefied gas, okay, and you want to compute diffusivity, okay, there is some expression which comes from Boltzmann equation, some finite term, and then you look for corrections, expansion over density, right? And for what you discover that they behave as the size of the system in some power n minus d. So for some n, it diverges. For 3D, and all these divergences aren't that dramatic. You can sum of them and get here rho cube logarithm rho. Not a big deal. You don't care much, but it's an analytic function. It tells you that there is no, this is the simplest thing, this is a diffusivity, but it's a non-equilibrium quantity, right? So you impose gradient and you compute flux. That was Dorfman and Cohen in 70s. It's an old works. We just recently rediscovered it with Levitov because of our electronic works, which tomorrow I will talk. But this is a correction on the third order, or in 2 dimensions will be second order. So that's the result in this trivial case, right? That's what for dilute gas you got. In equilibrium, no such things. Equation of state, regular in every order, just integer power of pressure of density is a regular expansion. But diffusivity, viscosity, it's non-analytic. And now we get it in turbulence multiplied by Reynolds number.
Tomorrow.